the difference between yesterday's, which was a modified Atwood machine, and today's, that this is a full Atwood machine. So they tell us from the beginning that it's a frictionless and massless pulley that's giving you some information that you can use for later. But at this point, just start with a free body diagram. I think that'd be the best way to go. And again, I want to walk around and see what kind of progress you can make on this one. Clockwise, all right, so we're going to say this direction is positive, like you guys have ever seen a clock. But we'll say you have. So if that direction is positive, then this way will be positive for that mass, and this way will be positive for that mass. This isn't the only way to do this. This is the way I have chosen to do this. If you want to see a different way, look at your book. They have a different way. Now, most everybody drew a free body diagram that was okay. But the only way it will go clockwise across the pulley is if M2 is greater than M1. Would you guys agree with that? So I'm going to draw M2G on this side and M1G on this side. I'm making M2 clearly greater than M1. Yesterday, you were given a piece of information to use in regards to the tension. You were told that if the pulley has no friction and no mass, then it adds no inertia to the system, and therefore the tension in the cable everywhere has to be the same. But you can't just draw any arrow. It was clear that one weight accelerated upwards and the other weight accelerated downwards. So I need a tension that is bigger than the weight on this side, but less than the weight on that side. But the two tensions have to be the same. That was my reasonable attempt to do that. Now, you just watched it happen. Is this a first law problem or a second law problem? It's a second law problem. So on this side, net force equals M2A. It accelerated. Look, I'm not going to break it up into the X and Y direction. Do I have to worry about the X direction at all here? No. So, I mean, let's not waste time. The left side, similar. Net force equals M1A. So now your next job is to just put the forces in. On the right side, I'm going to have M2G minus T equals M2A. Right? Downwards is positive. So what's it going to be on the left side? What's that? Tension minus M1G, and that's going to equal M1A. All right, I saw it in this class, so I have to address it. Can I just cancel out the M1 on both sides? No, I can't do that. There's no M in this term. The only way I could do that is if there's an M in every term on both sides, and there's not. So no, that's not going to fly. Now, I want the acceleration. I have two equations and two unknowns. So those unknowns are the accelerations and the tensions. So you got to get rid of something. Get rid of the tension. We want acceleration. That's what you were asked to find in the problem. Find an expression for the acceleration of the system. So I don't know how you want to do that, but you have two places that you can choose to do that from. Here and here. Now you have options. How will you do this? You want to eliminate tension. You could solve both of these for tension and set them equal to each other. You could solve one for tension and plug it into the other, or you could add the two equations together. Which one would you like to do? Yeah, if you have an equation that has one of them positive and one of them negative, adding the two equations together is the easiest way to go because these two are going to cancel out. Well, sum to be 0. So I will have m2g minus t plus t minus m1g. That's all on the left side. And on the right side, I'll have m1a plus m2a. Now, obviously, the negative t and the positive t add up to be 0. So I get m2g minus m1g equals m1. I'm going to factor out the a, because I know I'm trying to get a by itself. So I'm going to factor out the a. It's the same in both terms. So now I'll divide both sides by m1 plus m2. That's it. It's not much here, guys. I could do something here that might be helpful. I'm going to factor the g out, okay? So I'll get m2 minus m1 over m1 plus m2 times g equals a. Now, this part, you have to nail this, because then they're going to ask you questions like, what happens if M2 and M1 are the same mass? What did happen? When I put the same mass on both sides, what happened? They didn't move up and down. They just stayed there. Does this back that up? If M2 equals M1, what will the top be? The top will be 0. Will there be any acceleration? No. So this is how, in a test, because this is how I'm going to put your test, this exact kind of question. I'm going to have a question before you have to derive all this that says something like, you hang the same weight on either side of a pulley. What will be the acceleration? And you'll probably say 0. I hope you do, that it won't accelerate. And then I'll say, derive an expression for the acceleration of the system in terms of M2 and M1 and any fundamental constants. That's what this is. And then there'll be a follow-up question, and it'll say, does your theory support your guess for the earlier question? And you'll have to point to this and say, yeah, if M2 equaled M1, the top of this would be 0, and therefore the acceleration would be 0. You have to say all of those kinds of things if you want full credit. But you'll have to be able to derive this. And then there'll be the question like this: what if M1 is actually greater than M2? What happens here? What would you say if it were a test? Well, that's too bad, because when you have this test next week, if this is what you say, you're probably not going to earn too many points. What will this be if M1 is actually greater than M2? It will be negative. That's right. Now, that doesn't mean very much in physics except for direction. It means that the acceleration will be in the opposite direction. So M1 will be the one accelerating downwards, and M2 will be accelerating upwards, because our picture said that this was the positive direction. So if the acceleration was negative, then it will just go in the opposite direction. That's all it's saying, which is a big duh, because if the M1 is heavier, it's the one that's going to go down. So don't make it harder than it is, but this is all we're doing. I'm concerned about your capabilities here, so let's do why don't you guys do on your own just number 1, and I will check your work. All right, well, I saw some good work out there. So there's a few folks still having a bit of a struggle, but not much. 5 kilograms, no big deal. You had to choose a direction to call positive. Was it a big stretch to say this is the positive direction? No, it's a good way to go. I think it's going to go this way. I think in your diagrams, be careful. I saw some weird stuff here. If you're saying that this is 50, right, mg, then this has to be less than that so it can accelerate downwards. Right, they can't be equal. Make sure your diagram reflects that. If you're looking at the one that's on the table, well, this tension should be about the same size as this tension. Right, you should try and endeavor to do so. On your test, there'll be a grid, so you will have to make sure they're the same size. You don't have to make this one, like, you don't have to know what this is ahead of time. You just know it has to be less than this. So here, though, the normal force and the weight should be balanced. It's not accelerating up or down. It is going to accelerate to the left, because that's where the cable is. So from this point forward, it's a net force equals MA problem. Now, the box that's on the table, truthfully, I should say net force in the Y direction and net force in the X direction. But is it accelerating in the Y direction? Is the box accelerating up or down, the one that's on the table? No. So I'll hold on to looking at it, and I can write normal minus 50 equals 0. That's fine. But I'm not going to use this here. I don't need the normal force. There's no friction. But the other one is going to be tension equals M. I don't know, the M on the table, they're both the same mass. I'll just say MA. Or tension equals 5 times A. So here, I've got 50 minus tension equals MA. Made downwards positive to be consistent. And that's going to be 50 minus tension equals 5A. That's all there is to this. This doesn't have a whole lot. Now I could add the two equations together. I could do substitution. It's up to you. This one's already solved for T. So if you wanted to, you could just do substitution here and do 50 minus 5A equals 5A. It's your choice. Move that over and get 50 equals 10A, or A equals 5. Now, I didn't use 9.8, I used 10, because this is just a problem in the homework. It's not a lab. So if you use 9.8, you got 4.9 here. Now, if I want to find out what the tension in the cable was, well, I'll just go substitute over there and get that your tension is going to be 25 newtons. All good? Well, most of you look like you did a pretty good job here. Some of you, there were some troubles. I'm going to switch this up now. I want to use the same arrangement here, but I'm going to make some differences. First, the table is not frictionless. There's a coefficient of kinetic friction. This box is M2 and this box is M1. Everything okay? Everybody see the parameters? We'll assume that the pulley is frictionless, and this part's important, somebody gives the M2 a brief push to break static friction. Can you come up with an expression for the acceleration? This one's tougher, because now we got to deal with friction. So I'll remind you, dealing with friction, kinetic friction is equal to mu times the normal force. So start a free body diagram for the one that's on the table. Start a free body diagram for the one that's hanging. I'm still going to have weight downwards and tension upwards. On the box on the table, I'm still going to have tension to the left. I'm still going to have weight downwards. And normal force upwards, all still the same. However, if I give the box a shove to the left, what direction will friction be acting? So I need to draw an arrow to indicate friction is to the right. Now, here's the thing. I don't know how big the friction is. So I don't know if this is accelerating. I don't know if this is moving at a constant velocity. I don't know if it's speeding up or slowing down. I don't know any of those things. But remember, if you don't know if it's a first law problem, you have to assume it's a second law problem. So we assume it's a second law problem. And it's going to be second law for both masses. Everything else is going to work out the same. So let's start working out the relationships here. On the mass that's hung, can you write that down? What's going to be the net force equation for the mass that's hung? Yep. Yeah, perfect. How about the one on the table? Can you give me that one? Just give me one of them, either X direction or Y direction. Can somebody else give me the Y direction? Oh, come on, somebody. Really? No, you've been great. It just bothers me because I know people know it. They're just too scared to talk in front of a group. It's kind of creepy. There's only 19 people here. Yeah. There we go. All right. This is it. This is all the stuff. Are the two boxes connected together? Like, is there a string connecting them? So we know that they're going to have the same acceleration. So that's the same for both. You can still work this problem the same way we've worked the others. I can eliminate t between these two. I can add these two relationships up. I'll get, just take this guy. Oh, I guess I can't take that guy. Oh, I just have to rewrite it. Take this one, t minus f equals m2a. I can add those things together over there. The t's will cancel, and I'll get m1g minus friction equals m1a plus m2a. Now, the problem is that I've got F friction in the answer, and I'm pretty sure I'm going to have to work this into the answer. You've done friction problems before, and there's one in the homework just like this. I was trying to get you a head start on it. I think you should be able to do this one for me tomorrow.